Good afternoon, everyone. This is one of the very last sessions of this ISMAR 25. My name is Guillaume Moreau. I'm from IMT Atlantic in France, and I'll be chairing this session dedicated to visual cues and perception. As every session chair, I'm entitled to be the timekeeper, so I hope I'll have opportunities to play with this bell. No, just kidding. So we can start with the very first paper towards augmented reality support for swarm monitoring, evaluating visual cues to prevent fragmentation. And this paper will be presented by Aymeric Hénard, who's basically from the same university as I, but this happens. Aymeric, the floor is yours.
Thank you. Nice to meet you all. I'm Aymeric Hénard, and I will present you the work called Toward Augmented Reality Support for Swarm Monitoring, Evaluating Visual Cue to Prevent Fragmentation. First, to give you some context, a swarm of robots is a set of autonomous robots that self-organize by interacting locally without any centralized control. In swarms, collective behavior emerges from the interaction between robots, but none of the robots is aware of the overall behavior of the swarm. In that context, each robot has an individual behavior based on its current states and its nearby environment. In this study, we will use as a behavior of our robots the MECAS model. It has a distance-based perception systems with a blind spot at the rear of the robot. Consequently, the robot perceived are in the field of view and the other are outside, so they are not perceived. Our robots move using a virtual forces-based systems, so multiple forces will be applied to the robots depending on its states and the neighborhood. These forces are combined into an acceleration that will modify the velocity of the robot. To each of these forces, it is associated a multiplier coefficient, which can be adjusted by a user in order to modify the robot behaviors. By modifying the robot behavior, we can change the overall behavior of the swarm, and in that context, obtain multiple swarm behaviors, as the one you can see on the presentation. By incorrectly modifying this parameter, we can also obtain a fragmented version of these behaviors. So fragmentation is a weakness of autonomy in swarms. It corresponds to a loss of communication and coordination among the robots. Basically, its swarm is divided in multiple groups. If unwanted, fragmentation can cause the task to fail, so we don't want the swarm to fragment. So one solution is to ask an operator to monitor the swarm to prevent fragmentation. But monitoring a swarm is kind of complicated, so we want to help the user to do it. As many swarm behavior emerges from spatiality and spatial dynamic of the swarm, we want to keep this aspect visible for the user. So one great solution to go through it is to use localized AR visualization, which can allow us to add information without hiding what the swarm already conveys. So that's what we will be present in this study. In this study, we will answer two research questions. The first and main one will be, how do visualization based on the robot behavior affect human's ability to prevent fragmentation? And our second question is, how do different swarm behaviors affect the human ability to prevent fragmentation? This second question will allow us to verify that there is a real need to help the operator. So we will be evaluating three visualizations in this presentation. Why three? Because we want to test the hypothesis made by colleagues saying that explaining certain aspects of the behavioral model of the robots could facilitate understanding of the swarm dynamics. To represent the behavior of the robots, we will use the PDI loop from multi-agent systems, which represent the behavior into perception, decision, and action aspects. In this study, our visual cues will be displayed at the robot level, so on each robot, and systematically. For the first aspect, so the perception, we will display the connectivity of the swarm by displaying links between interacting agents. The link syncness will change depending on how far two robots are from the break. If they are near from the break, it will be thin, and if they are far from it, it will be thick. Concerning the decision aspect, we want to show why the robot moves, so we will show the force that both influences the direction of acceleration. To do this, we will add as a visual cue an arrow above each of the robots. This arrow will be in a different color depending on which force is dominating the movement. And it will be white if none of the force dominate the movement. Moreover, the arrow points toward the same direction as the acceleration vector. And finally, for the last aspect, so the action part, as our robots only move, we will display the direction of the robots. It's a visualization which is frequently used in robot swarms, but rarely evaluated, so it will be the occasion to test it. So in this study, we will compare this visualization with a reference condition showing no visual cues. We will also compare the 4 behaviors obtainable with our model to answer the second question. So we did a user study. We asked 51 participants to watch clips in VR, and they must answer a question after watching a clip. So a clip is a small extract of simulation which is replayed in front of participants. The procedure is the following. So first, the experiment is introduced to the participants, and then they have to perform two tasks. The first one is the anticipation task, and the second one is the appropriate control selection task. Finally, participants have to fill a questionnaire in order to us to gather subjective data. So the first task, the anticipation task, participants have to watch clips, and after the end of each of them, they have any time they want to answer the question, will the swarm fragment? They can answer by yes or no. Beforehand, they are advised that if a fragmentation is to occur, it will be shortly after the end of the clip. For the second task, it's the same principle, but the question changes. This time, they have to answer the question, what changes should have been made to the swarm to prevent it from fragmenting? They can't answer by yes or no this time. To each of the clip, we predefine 2 choices, and one choice prevent fragmentation, and the other one don't. But in all these tasks, they do not see the consequences of their choices. They can't learn from their action. In these 2 tasks, we gather correct answer and answer time, and we also, during the questionnaire, collect some subjective data, and notably, we retrieve their opinion on which visualization they found the most helpful for each task. Now let's look at the result of the behaviors. So for the first task, anticipation task, one of the behavior was easier to anticipate, so the densification behavior. And for the second task, the appropriate control behavior, it's also densification, which is significantly easier to correct than swarming. But the most important result for this presentation is that looking at the performance of the participants, fragmentation are difficultly anticipated and corrected. So we prove that an help must be provided to the operator. Now let's look at the result for visualization. So for the anticipation task, we were expecting that links will help to anticipate fragmentation, as it gives an hint about the connectivity of the swarm, so it may help to anticipate. Looking at the result, we found that links is significantly more useful than dominant force and direction, but no improvement was found compared to the reference. Looking at the subjective results, we found that 3/4 of the participants found the visualization of the link to be the most useful to anticipate. Now for the second task, this time we were expecting that dominant force will help to prevent fragmentation, as it gives an hint about why the robot is moving like this. Maybe it can help user to understand how to change that behavior to modify the overall behavior of the swarm. Looking at the results, we found that no visualization improved performance, and the subjective results show us that half of the participants found the visualization of the dominant force to be the most useful. So, overall, the visualization show no significant differences compared to the reference, but the user feedback is in line with our initial expectation. Links were preferred for the first task and dominant force for the second. So we can expect some improvement to be made. For example, for the visualization of the links, maybe it conveys the connectivity of the swarm, but not the dynamics of the interaction, which could be the right information to convey to anticipate fragmentation. Concerning the visualization of dominant force, sometimes there is a lot of information to gather. Many arrow pointing in every direction. It can be really difficult for people to gather any interesting information. So, in this study, we try to show robot level and systematic visual cues, but it seems to overload the user without providing any significant benefits. Users don't seem to intuitively infer the global state of the swarm from the individual robot data. So what next? We will try to aggregate and filter information, focusing on swarm level or conditional display to balance clarity and detail, and maybe will help to prevent fragmentation. I will leave you with these takeaway messages. Thank you for your attention, and feel free to read the paper if you want more information. Thank you.
Thank you very much, Eric. I didn't even have to ring the bell, so we have plenty of time for questions from the room. See one over there. Okay. The mic is coming.
Thank you. Thanks for the talk. I was wondering, so in psychology, there's been these old studies on what they call pre-attentive features. Do you know about these?
Can you repeat?
Pre-attentive features.
Pre-intended feature?
Pre-attentive, so things that come before you actually start to pay attention, and your brain can process these automatically. And these have been listed there: color, motion, direction, etc.
Okay.
And they can work in tandem and complement themselves. So that could be a fun way to start looking for visualizations that actually do not overload, but actually are processed automatically by the brain for free, basically.
Okay, thanks for the advice. I didn't know about it. Yeah, thank you.
Okay, then I have a question. Did you consider displaying future condition predicted future condition rather than some kind of present condition?
So visualization that gives the prediction of the state of the swarm. Yeah, we are looking at it, but first of all, we wanted to just give more information and to try if the user can interpret it by itself, to avoid misinformation from the system, because if it failed to predict the state of the swarm, it will be really dangerous for the task or not. So we want to try it first, and if we have no choice, try to predict it. Yeah. Thank you.
Thank you. Any other question from the room? No? Well, thank you, Emeric, again.
Thank you.
As soon as you're ready, you can go.
Okay. Good afternoon, everyone. My name is Jiahong Luo. I'm a PhD student from Beijing Institute of Technology. Today, I will introduce the work on cross-media color appearance reproduction in optical see-through augmented reality. I will introduce my work through the following aspects: background, experiments, analysis, and conclusion. The first part is the background. Optical see-through augmented reality, or OSTAR for short, allows light to pass through the glasses into users' eyes directly, So the OST-AR blinds the virtual images with the real world at optical level. It has a lot of advantages and widely used in industries, smart wearable, healthcare, and tourism. However, here is a challenge of the OST-AR, that the AR image is easily influenced by the ambient light. Many previous methods had tried to correct the colors at colorimetric level. However, the chromaticity alone can't fully capture how people perceive the color in AR. And we must focus on the color appearance reproduction because it takes the environmental factors into account. The color appearance reproduction means using the color appearance model to predict how different factors influence the way we perceive color. And the key factor here is the chromatic adaptation. It's our eye's ability to adjust to the changes in the white point under different lights. And the OST-AR blinds the surface color from the real world and the self-luminous color of the virtual display. However, for most of the color appearance model now, the data are only based on the surface colors, which is very different from the OST-AR. What's more, the chromatic adaptation in AR hasn't been studied systematically yet. So these are the gaps we aim to fill. To conduct the cross-media color appearance reproduction, we conducted a series of color matching experiments. Color matching means adjusting one stimulus until it looks the same as the reference. In our setup, we use an OST-AR head-mounted display as the reference and another mobile display as the adjustable one. We measure the transmittance spectra of the AR and the primary spectra of both two displays. They both have similar color gamuts like sRGB. And for background, we use an immersive lighting booth. And the color has 4 correlated color temperatures and 2 more colorful ones, each at 2 luminance levels. So there are 12 backgrounds together. And for color stimulus, we set 5 chromaticity points at a fixed level, a luminous level. And the reference is the blind of virtual stimulus and the background. So different combination will give different reference stimulus. There are 16 reference stimulus together. All the experiments were conducted in a dark room, and the stimulus and the background are presented in a random order. The participant should adjust the stimulus on the mobile display until it looks the same as the reference. Now, here are the results of our neutral illuminance experiment. We can see from this photo that the red circle represents the reference stimulus, while the red crosses means the average, the match result. We can see that there is a color mismatch between the reference and the average match the result. However, in neutral illuminance, people are expected to get the complete color adaptation. This means that the matching result should equal the reference color. However, there is still a noticeable color mismatch between them, and the color difference is more pronounced at higher luminance level. We suggest that there may have some difference between the internal white point of these two display media. So we calculated the CCT. It means the correlated color temperature of different media. And we can see from the table that the OST-AR has slightly higher CCT of internal white point compared to the mobile display. And this difference is more pronounced at the higher luminance. So there is indeed an internal white point difference between the two display media. And here are the results of our non-neutral illuminance. The top is the low luminance and the bottom is high luminance. Different columns represent different environmental setup. And we can see that across all the environmental setup, the reference stimulus is different from the average matched result. This means that the chromatic adaptation in OST-AR varies between different illuminance conditions. So based on these results, we came up with a new 3-step chromatic adaptation transform. In traditional adaptation transform, they only change the light in illuminant A, the color in illuminant A directly to illuminant B. And in this way, they ignore two very important factors. The first one is the chromatic adaptation degree of different lights. And the second one is different internal white point in different media. So in our method, we take these factors into account. In step 1, we fix the media and change the light from illuminant A to a baseline. In step 2, we fix the light and change the media from medium 1 to medium 2. And in step 3, we fix the media, change the light from the baseline to illuminant B. So in this way, we can get how the initial color looks in a new light source and the new display media. This is the first time we take these two key factors separately together. And after using our three-step cat in the neutral illuminance, we can see from the table that the color difference between the matched and the optimized result became smaller. Here are after using our three-step cat in non-neutral illuminance, we calculated the chromatic adaptation degree by a memory wet point matching experiment. And the chromatic adaptation degree are shown in the figure. We can see that the OST-AR has more complete chromatic adaptation than the mobile display. And both two displays have higher chromatic adaptation at higher luminance. What's more, the chromatic adaptation varying with the background colors. By using this data in our three-step cat, we calculated the color difference and the non-neutral illuminance, and the results are shown in the figure. Our result is the light blue, and we can see that our three-step cat effectively reduced the color difference and improved the color prediction accuracy. So to further test our three-step cat, we conducted a subjective rating experiment. The participants should rate the color difference between AR and the mobile display using a 5-point scale, from imperceptible to very noticeable. And the mobile display stimulus was with or without a three-step cat. We used 3 new AR virtual stimulus and 8 light sources. And the rating results were shown in the figure. We can see that after using our three-step cat, there is a higher color, the rating score is much higher, and this means that our three-step cat has higher color consistency across the media. So in conclusion, we conducted a series of systematically study of cross-media color appearance reproduction in OST-AR. And theoretically, the OST-AR achieves more complete visual adaptation than the self-luminous display. And technically, the proposed three-step cat model will resolve white point shifts across media and handles the incomplete adaptation under non-neutral illuminance. Our experiments advance the theory of visual adaptation and enhance the realism and the immersion in the OST-AR. Okay, that's the end of my presentation. Thank you for your listening.
Thank you. We are far ahead of schedule. So, any questions? There's one question in the middle.
Thank you for the talk. It's a challenging topic. Color is, my personal opinion is, color is a very challenging topic, so congratulations on that for doing it. My question is related to the participant capability of identifying contrast in colors. So before doing the study, did you do any pre-study or pre-evaluation of participants, whether they were, or to what level they were able to differentiate or differentiate among the contrast, so that the variability among the participants might not have impacted your study results?
Sorry, could you please repeat speak up a little? So,
Okay, I'll try to explain this. Each individual has their own capability of differentiating contrast in colors. Okay, so I'm asking if you did a pre-study or evaluated the participants regarding their capability of identifying or the contrast in the colors, so that might not have impacted the results of the study.
do you mean that the participants has already practiced the experiments before? They have the experience?
Not that. I'm trying to ask if each individual has their own capability of identifying contrast. Maybe I can catch up later with you. That's okay. Thank you.
Okay, I will think about it and get back to you after the presentation, because I can't hear because if the...
Due to the
I'm sorry.
Thank you.
Other questions arising? For the sake of the record, we hear very bad on the stage because the loudspeakers are on the other side. That's why it's very difficult to hear the questions. Still, I had a question. You said that errors were getting worse as far as luminance was increasing. So the ultimate challenge is, how do we go outdoors with your techniques?
Our experiments focus on the indoor experiments because the illumination of our experiment is not so high. And the indoor, for outdoor, the color appearance, it seems to more hard to see the AR object clear. This is, and I think that in my further study, we may try to use this model in an outdoor environment to test the result. Okay, thank you for your question.
No question arising? So let's thank the speaker again.
All right. Hello, everyone. Hope you can hear me. Let's see. I don't need that. So I'm presenting this work on behalf of first author Kang Yu, who completed a Master's of Science with my lab at UCSB and is now in visa negotiations with another country. And that's why he can't be here today. This project had long been a topic of interest in my lab, and I'm thrilled to present it here today. So the overarching question is, what is the cost of switching back and forth between the virtual and physical realm using optical see-through displays in particular? In AR, we often consider physical and virtual objects in quick succession. Let me give you an example. Here in this AI-generated sketch, a user is looking at a building facade, physical world, and there may be an annotation to the side. In order to compare maybe architectural kind of features with the art history in the annotation, they have to go back and forth between the two. So what effects come into play here? One thing that comes to mind is divergence accommodation conflict, or VAC. And in this case, it's actually a special case of the VAC, namely involving physical and virtual focal planes, right? So the physical object under consideration is at one focal plane, and the virtual annotation potentially verged at the same distance, if the author of that annotation has done it like that, is at another, namely the displaced focal plane, right? Let me warn you right now, leading into my talk with this is a little bit of a red herring because for this work, because even though we set out to explore and control for exactly this phenomenon. The true costs, as it turns out, actually lie somewhere else when switching between virtual and physical objects. Just remember one thing from the slide. The VAC exists both between the physical world and the annotation in the virtual world, but could also be as well just among the virtual annotations themselves, right? I mean, most of the work in virtual in Virgin's accommodation conflict is actually studied in VR more than AR. So maybe we will see in the end why that is the case. All right, let me give you another example, motivating example. This one is from work in my lab on mobile augmented reality. We presented this work at CAI in Yokohama earlier this year. And this was users taking part in an AR treasure hunt where the search targets were either physical Philips Hue lamps or virtual replicas that we try to make appear as closely as possible to the physical thing. Okay? And as an informal result, that is not really in the paper, we found through user interviews that some participants, when they had found one, say, physical lamp, they first looked for other physical lamps, even if some virtual lamps were closer nearby. So we dubbed this postulated phenomenon virtuality inertia, a tendency to continue searching for the next item within the same virtuality realm as you had before. Okay, so we were interested in this. And we tried to do like several pilot studies on this. In fact, this went on like over more than a year. So we started with physical ping pong balls and had a sequence of numbers on them, right? So, and some of the ping pong balls were physically labeled, some of them were virtually labeled. And we were trying, and this was a little bit easier than with the Philips Hue lamps, keep the virtual and physical appearance as close as possible. And there was, it turned out, a heavy cost of switching between the virtual and physical realms. Okay, it was always taking longer to do sequences that involved such switches. All right, so and that's this work that I'm presenting here now identifies and studies this phenomenon in more controlled settings. So research questions, what is the impact of switching between physical and virtual objects in a task that requires attention and focus in quick successions, right? So it's actually a selection task with this sequence numbers. And then we are interested in what costs are involved. And there could be behavioral costs of the user, changing something because of certain circumstances, or could be physiological costs. So the VAC would be like part of the latter, right? Or other causes of eye strain. And then we also wanted to know, is there maybe a difference between different transitions from virtual to physical versus physical to virtual? Okay. So in order to control this a little bit better than with the ping pong balls, which were already promising and already easier, this is even like more simplified. What we did is a wall poster, and balls became circles on this wall poster, and we did an overall circle so we could keep distances a little bit more aligned. We had as conditions purely virtual sequences, purely physical sequences, and mixed. And we did this in two distances. The first distance was carefully chosen to be at the focal plane of our display, which was the Magic Leap 2. That is, I think, 74 centimeters or something like that. And we kept the two distances, also the appearance of the targets, so that the subtended visual angle is the same, right? So the appearance to the person with a bigger poster and a longer distance is the same as when you're close by or with a smaller poster. Okay, so this way we could isolate the VAC effect, actually. So let me show you what this looks like. I can't show you the entire sequences, but so here is the virtual condition, purely virtual. It's always difficult to capture mixed reality, so when you get to see the physical, you will see registration artifacts that are quite a bit bigger than the person actually doing the study saw. There's no registration artifacts here, because this is all virtual, but on the physical backdrop. Okay, but the numbers are all virtual on the circle planes. Okay, so this is all virtual, so let me speed this up. So this is all physical. So if you like take away the registration artifact here, which looked again much better for the person that did this, then it looks pretty much the same. But now the numbers are actually physically on the poster. Okay. And then the most interesting condition is the mixed condition. And here's actually good now that they have the slight difference of the registration artifact, because you can see 8 was physical, 10 was virtual, just from the registration artifact that you see here. And next one, 11, takes already a little bit longer to find for this participant. There it is. It's a physical one. And so on and so forth. And so there are 25 numbers in this circle, and so we can change the order. The physical ones obviously require printing different numbers. The virtual ones can be arranged on the fly. So then just to show you as well that the visual subtended angle looks the same with the far condition. This is what it looks like in the far condition. Let me actually speed up and give you the mixed condition there. And yeah, there's slight differences here, particularly in this particular sequence between maybe the lighting of the physical and virtual number plates. But we tried to keep it really as close as possible. We did an enormous amount of pilot studies on this. So that's the setup. All right, user study design. We have 6 conditions, right? 2 times 3. There's 2 distances, 3 virtuality conditions, all virtual, all physical, and mixed, so 6 total. And then for, remember research question 3, we were interested in transitions as well. Obviously, there are 4, virtual to virtual, virtual to physical, physical to virtual, and physical to physical, okay? And we use Latin square counterbalancing of the order of conditions. This is how it actually was the full design of the study. We had 36 participants from our human subjects pool at the university. They were self-identified, 25 male, 11 female, and so on. And this was the structure. So we introduction of what I was doing, agreement and consent procedure, demographics and collection of like pre-questionnaires, pre-study questionnaires, some training, and then these blocks in the middle, right? So, and we had 2 blocks each of the 6 conditions with different permutations of the numbers. And so that makes for a total of 300 trials, because there's 25 trials, 25 numbers to select for each of these 12 conditions. How do I get to 300? Times 6 times 2 is 12, and 25 targets is 300, exactly. Yeah, good. So results. Physicality first. So you see a big penalty, right, for the mixed condition. So that was what we're interested in. And the penalty is both in total time spent for this, as well as in accuracy. So that's interesting. And in terms of the 2 distances, there were much fewer findings. But we were on the lookout for the VAC, right? Remember that? We did find an interaction, a significant interaction between virtuality and distance regarding selection accuracy. So accuracy, not time. And we have a higher accuracy in the near condition than in the far condition. So if you look at that right there, now you remember that VAC actually happens also within virtual conditions itself, right? So we have between the one that happens at focal plane and the one that is 3 meters away, which we chose, by the way, in order to be representative for mid to far level interactions. So then you see that there is a penalty in terms of accuracy for the selection between these 2. Now these are the results on the transitions. The virtual to physical transitions took the longest to complete, followed by the physical to virtual transitions. So again, it's the ones that bridge the virtualities, right? And then at comparable cost, it's physical to physical, and last virtual to virtual transitions. And we collected eye gaze on this as well to get to some explanations of what might be at the heart of this and what's going on here. So participants did exhibit more active and complex eye gaze activity in the mixed and also in the far conditions. So here we have the number of items that were dwelled on for a certain period of time, okay? And the number is higher for mixed and for the far conditions. And interestingly, so they are, their saccade activity was accelerated. They did more of them, right? But they overall took longer. So they're clearly more inefficient. So virtuality inertia, as I defined it before, is probably one of the culprits. And we saw that here as well when we tried to actually look for patterns in the eye gaze. So people actually, when they were, the last two selections were virtual, were trying to scan ahead, is there another virtual one? And that requires that they can actually tell, right? So if that difference would go away, this behavioral difference would actually have to go away, which is interesting. But for designers, we will probably always want to delineate and distinguish virtual from physical entities, at least for some cases. All right, so this is the summary overview. I went through all of these results already. Much more findings, many more findings are in the paper. I don't have time for them here. So let me just try to wrap up with discussion. So target physicality and distance significantly affect performance and user experience. There was a clear penalty for our selection tasks with mixed virtuality involving like physical and virtual targets. Tasks with all virtual objects were somewhat easier and less cumbersome than those with all physical. That was a side effect. And then the main cost of this virtuality switching that we could find was not the VAC. That was actually just a very small component. We did find that as well. But behavioral adaptations of the people that actually did see some difference, be it through tracking or be it through visual differences that they could still see. And one of them is virtuality inertia, as we dubbed it, as reaction to being faced with the challenge of back and forth focus and attention switching between virtual and physical targets. So definitely this is a concept that we want to further explore. And we think that these results are a first step towards more comprehensive modeling of user cognitive and psychophysiological phenomena associated with switching between virtualities. So that is what I have. Thank you so much.
Thank you very much, Tobias. I see questions from Stephen up in front. Second row. Second row from the front.
Yeah, thank you for a really neat study. It's a pity your student wasn't able to go out and present it. So I have two questions. One of them is that you have a wide range of people, including folks at the upper end who are probably have very little amplitude of accommodation left, and younger folks who actually can differentially focus. What kind of difference might you have seen between, if any, between the performance of the older participants versus the younger ones?
You say to postulate what happens when there are no noticeable differences.
No, I'm saying that your older participants probably have no amplitude of accommodation left.
Oh,
right.
I see.
So their eyes are presbyopic, right?
You say older participants.
The older ones, you got some 45-year-old ones.
I really feel with the previous performer, I can't hear anything here as well.
Yes.
Either. So yeah, so that's interesting. Unfortunately, our audience was on the young side. I think I have it here.
You had
so
a 45-year-old in there.
Yeah, we don't have many cases.
Yeah.
So look, the average is 22 years.
Right.
So we didn't have many older people. I don't think we have enough statistical power to actually say something about that. But that would be a great future point to look into. Because you're right. I mean, these people would not actually have the VAC or would have different VAC kind of accommodations there. But as we said, I mean, the VAC doesn't really play a big role here anyway, right? So I don't think there will be a big difference between older people and younger people. I think they all can distinguish what is virtual and physical still.
So in terms of that, you have these printed posters, right? Did you think about instead using a projector or an actual display physically on the wall where you could, in fact, make it jitter a little bit, right, in the way in which probably was happening in...
Yeah, we did think about that. I think it's future work. It is... would be great to have this particular knowledge of what is physical and virtual taken out of the equation, and then we're back to like what are the physiological changes, right? Which was our original question. But I think the interesting bit about this work is actually that in the current state of affairs, the behavioral changes by far outweigh the physiological phenomena.
Because the displays aren't good enough.
Yeah, last, more, whichever, the closest. We have time for one question, unfortunately, so this will be the last one.
Hopefully you can hear it. So in the physical conditions, there was still a virtual ray and a virtual highlight, right? So do you think that that could play a role, even if you're not like attending to those things exactly, that that could play a role in making even the all physical condition work worse than the all virtual condition?
Yeah, I mean, we actually asked our participants about that they, but they felt that the controller interface was very nice, right? I mean, what else would you do? There is no physical way that you can actually use. You have to use eye gaze for it, for example. But that has its own problems on that, and it would interfere with the eye gaze that we wanted to actually for that. So I don't think it had that big an impact, honestly. The starting point was that we actually see this as a platform that allows us to experiment more with multimodal interfaces and different
Maybe future study could use a laser pointer and lights on the wall instead of stuff seen through an head, just like similar to what Steve said. Yeah.
Okay, thank you again.
So, thank you for introducing. So, hi, everyone. I am Haesung. So today, I represent my work, and our research explored human and AI are aligned when it comes to the driving accident. So to begin with, I'll explain our motivations. So these days, there's a lot of talk about AI, and we can feel the AI achieving the human level performance in many domains. So the researchers use this AI to predict future risk in safety critical domains, such as the accident preventions and medical diagnosis. But if AI predict the future by attending to different cues than humans do, so imagine the pictures like in the right. So in this situation, you can expect that an accident will happen soon. In these critical situations, we are likely to focus more on the critical object, like a truck. But if AI assistant is focusing on totally different, then no matter how accurate its performance might be, the system is become unreliable and potentially dangerous. So this is why attention gap is matter, and we have to identify this attention gap to guarantee safety and trust and collaborate with AI. However, there is no benchmark for measuring this alignment in risky situations. So here is a video we use in our experiment. So in the left figure, you can see the top view at the final moment. Initially, the left side is a normal load and the human driver. The right is the cliff exists. Driver intend to take us to the safe road, but suddenly the tree fell down and blocked the safety road. So in these situations, driver must choose between two critical options. The first one is collide to the tree, and second option is the fallen into the cliff. So let's try to predict ourselves. This is 2-second video, and pay attention where the car will go, left or right. So very short clip, so let me show again. So in this short clip, so you might have something interesting that the steering wheel turn right and the driver gaze remain the left. And this left is the direction of the car will go. So the question is coming that do AI look in the same way we do? So this brings us the two research questions. First, can AI models reach human-level future anticipations? And second, when making these predictions, do AI models pay attention to the similar visual features as humans? So in the figure in the below, you can see our overall experimenter. So focus on the blue line first. So human and AI watch the same videos and make predictions. So we compare this prediction using some F1 score. So this process benchmark the prediction ability both human and AI. And beyond this performance, we want to find their visual attention differences. So while doing the AR predictions, we can use some eye tracking to extract some visual features. And for models, we can use some explainable AI method to where AI focus on. So using these visual attentions, we compare with some statistical test. And then this process tell us whether there are difference in attentional patterns during predictions. So in order to start our experiment, we built our own data set. The first 71 human driver driving in the dilemma situations, and each recorded video trimmed 8 seconds end of the final moment. So using this trimmed video, we eliminate 1 second removed to avoid the trivial anticipation. And using the remaining 7 seconds, we divide into the 5 time segments. This allows us to track how prediction accuracy evolve over time. So our focus is comparison of human and AI. So we recruit 30 human participants and use the 6 AI models. So in particular, AI models, so 2 types of AI models we used. The first one is the vision-only model, so LesNet-based and autoencoder and transformer-based. And second thing is the vision language models that, like GPT and Gemini, this architecture combines visual and textual processing for enhancing reasoning. So this have a powerful advantage that we can provide a detailed text instruction to guide their predictions. So here is the most important part of our work. So measuring visual alignment is quite tough. So we define the first 5 area of interest and track this through the videos. So, and using this AOI, we specifically employ the group-specific method to extract attention patterns. So look at the figure in the below. For the humans, their gaze extracted from the eye tracking. And then with this gaze, we can apply the Gaussian corner to generate the salience map. So, and then this salience map linked according to the predefined AOI. And for the vision models, we use the explainable AI called GradCam. So using this GradCam, we can get some salience map and we linked to the same way as the humans. And here is the tricky part. We use the API-based vision language models. So actually, we cannot access their internal weight. So we developed some new method called the AOI shape. So, but due to the time limit, I can go into the full details. But in short, we apply shape to quantify how much each regions contribute to the predictions. And here's the result about the prediction ability. So in the below figure, you can see the x-axis is the time sequence, and y-axis is the performance scores. And the red one is the humans, and blue one is the vision model, and the green one is vision language models. So at first glance, the all group performance overall increasing as time passed. So this is trivial. So more visual informations lead to the better prediction. And the early period, look at the green boxes, you can see the blue line, vision only model outperformed the humans. But after T3, the 3 seconds before the final event, the humans outperforming the AI. So, and remarkably, the performance gap narrowed over time. At the final moment, you can see AI achieve the human level. So we can say that the AI can see the dangers at the final moment. But here is the tricky part and interesting part. So can AI actually see the dangers like us? So to go further, we check their length changes. In other words, we check the visual priority. In the below figures, you can see x-axis is the time sequence and y-axis is the length. So lower length is more important. And for example, on the top R1 is the top priority. So in the early stage, in green boxes in each figures, humans focus on the load, but the AI models doesn't focus at all. And most potentially hazard comes the last part. So in the last part, blue box, human reallocate to their threat. Like here is the tree and cliff. And VRM also increase the cliff, but it is not enough to compare to the humans. And vision only models does not change at all. So next, we examine this finding through some correlation. So look at the below figure. X-axis also time, and y-axis is the correlation. Here is the red is the humans, and blue and green is the AI. So previously, we saw that both human and AI accuracy improving over time. But here you can see that there is no going as same pattern as inaccuracy. But in details, humans were remarkably consistent and high correlations, whether they predict correctly or not. But AI failed to follow human attention at all. Even the most closed the period in T1, when their performance matched to the human, they were looking somewhere completely different. So let me wrap up my findings. So first, we built a VR simulated emergency scenario data set and use it to benchmark for prediction ability and visual alignment. And second, so for prediction performance, both group prediction ability improved over time, and AI matched the human level predictions. You can see the best AI models matched to the humans. But however, their visual alignment has some huge gaps. And the right figure, you can see x-axis is the score, and y-axis is the correlation. Their correlation between the score and the correlation has something negative. So this result implies that the performance metrics does not tell us the model reliability in safety critical context. And for building trustworthy AI, we need human aligned attentions, not just the accuracy predictions. So moving forward, we are using some diverse dilemma scenario and use some advanced XI method and develop new metric both handling the performance and reasoning. Thank you. Yeah.
Thanks a lot. Any questions for Eugene? Yep.
Hi, it was a very nice talk. Thank you for that. My question is related to the contextual validity of your third condition, where you are using AI model with the text. So generally, in accident prediction, having a text-based predictive element is generally considered not helpful. So why did you choose that instead of something like an audio indicator, some prediction happening, and through the audio it's giving the feed, like giving the intimation of accident. So why text-based?
So you means why I use some specific car accident scenario?
Yeah, so why text-based? Because text-based prediction are generally not considered helpful for accident prediction.
Uh-huh.
So my question is, why did you choose that over some audio-based condition?
Yeah, in our experiment, we did not give some sound. We just only compared the visual patterns. So initially, this video has no sound. So our contribution is to compare the visual patterns. So we eliminate the audio. So is it answer to you?
It answers the part of it, but my main question is for why did you choose text? Because texts are generally not considered helpful for accident prediction.
Why I use this text? So in humans, we can give some instruction before the experiment, but in here, the vision model, we cannot give the specific instructions, such as the focusing on the dilemma situations where the car will go left or right. So we are using this vision language models to integrate to give some direction to the models as on text.
Okay, thank you.
Thank you.
No further question? Well, thank you very much.